¿no?
Sí, sí. Okay, so good afternoon, everybody. We today have the last plenary talk of the Congress. We have the immense honor to have Carlos Kenig talking in this plenary talk. And he has an incredible career, so I'm just going to give some highlights. He is a Lewis Block Distinguished Service Professor at the University of Chicago. He's president of the International Mathematical Union, member of the National Academy of Science, and his main field of specializations are partial differential equations and harmonic analysis, areas where he has made fundamental contributions. He belongs to the Calderon School, Calderon Sigmund School, and he has won numerous awards. So again, it is a honor to have him talking in this Congress. So Carlos, whenever you want, I leave the screen.
Well, thank you, Carlos, for the very nice introduction and for being here today. I mean, we've known each other since we were students. Also, I would like to thank the Scientific Advisory Committee for having selected me to give a talk in this very nice conference. And okay, let's get down to work. So, what happened here? Okay. In this talk, we will discuss some geometric analogs of the classical harmonic functions on Rn and their associated evolutions. Harmonic functions are ubiquitous in mathematics and its applications, arising in complex analysis, potential theory, electrostatics, and heat conduction. A harmonic function u in Rn solves the Laplace equation, Laplacian u equal to 0, where the Laplacian is the sum of the pure second partials. There's a well-known principle, the Dirichlet Principle, that says that harmonic functions are critical points of the Dirichlet energy, which is the integral of grad u squared with the 1/2 constant in there. The associated evolutions to the harmonic functions are solutions to the heat equation, dtu minus Laplacian u equal to 0, and the wave equation, d squared tu minus Laplacian u equal to 0. The geometrics analogs we will be discussing, which also have applications in physics, are the harmonic maps, which are functions u from Rn onto a manifold, M, the Riemannian manifold, and these harmonic maps were introduced in the early 1960s by Eels and Sampson, and they are also critical points of the Dirichlet energy, and they verify a nonlinear partial differential equation, which is the Euler-Lagrange equation of the Dirichlet integral for functions with values in M, and this is a nonlinear PDE because the u has to satisfy the nonlinear constraint to belong to M. When the manifold M is the round sphere in R3, the equation then becomes explicitly the Laplacian of u equals minus grad u squared times u, but you have to remember that u has to have absolute value 1 everywhere. So the point in the work of Eels and Simons in introducing these harmonic maps was to use them as a tool to study the geometric and topological properties of the manifold M. For example, they showed using the associated heat flow, which is called the harmonic map heat flow, that smooth functions from Rn into M can be deformed under certain geometric conditions on M into harmonic maps. This work of Eels and Sampson inspired Hamilton to introduce his Ricci flow, which led eventually to the proof of the Poincaré conjecture by Perelman. Uhlenbeck also contributed a lot to the theory of harmonic maps, introducing the bubbling of harmonic maps to study their singularities. It turns out that this bubbling phenomenon that Uhlenbeck introduced is universal, and is analogous to the soliton resolution, which we will be considering later on. Let me now turn to wave maps, which is the wave flow associated with harmonic maps. This is a very vast topic, and I will concentrate only, of course, on aspects close to my interests. There are several ways to define wave maps, U from R cross Rn into a manifold M. A formal one is you consider the Lagrangian, which is given by 1/2 of minus dtu squared plus grad u squared dt dx, and its formal critical points. And if you write the corresponding Euler Lagrange equation to this Lagrangian, you get the wave map equation. In the case when the manifold M is S2 and the dimension of Rn is 2, this becomes the equation d squared t minus Laplacian u equals absolute value of dt u squared minus grad u squared times u. But remember, u is constrained to have absolute value 1. And this is the wave equation associated with harmonic maps. And the static solutions, that is to say the solutions that are independent of time, are precisely the harmonic maps. The wave map equation is Hamiltonian and is time reversible. You can go both forward and backward in time. And there's a conserved energy. And the conserved energy is this 1/2 dtu squared plus grad u squared. This evolution is invariant under this scaling, where you scale time and space by lambda. And the conserved energy, this one, is also invariant under the scaling when we start from R2. And this makes the wave map equation an energy critical equation. And this is the wave analog of the harmonic map heat flow introduced by Ilse and Sampson. This, as I mentioned earlier, inspired the Ricci flow. And in the wave world, the analog of the Ricci flow is a system of Einstein vacuum field equations in general relativity. So wave maps are natural geometric wave equations, which also have their own physical meaning. They arise in physical models in particle physics, in gauge theories like nonlinear sigma models, and they're invariant under scaling, rotation, but they have a further invariance, a space-time invariance under Lorentz transformations. The theory of the Cauchy problem for the wave map equation, let's say with a target the sphere, for small data in the energy space was developed in some groundbreaking works by Tataro and Tao around 2000, while a theory for large data in short time was developed by Stervens and Tataro around 2010. When the target manifold M is a surface of revolution and n equals 2, there are special classes of wave maps which respect symmetries. For example, when M is S2, we can consider wave maps U that have the following property: U composed with rho equals rho to the k composed with U, and we call this the k equivariant wave maps. Here, k is a natural number, and rho is a rotation of R2, which induces a rotation of S2 by keeping a fixed axis. Thus, the wave map expressed when it has this kind of invariance can be expressed in polar coordinates for R2 and for S2 as the following map: T of the variable TR omega is sent, T is sent to T, and R omega is sent to a function psi of RT, and omega is sent to K omega, where K is the K equivariant index. So this induces a nonlinear equation for psi, which is the following nonlinear wave equation. The second derivative of psi minus the second derivative in r of psi minus dr of psi over r plus k times the sine of 2 psi over 2r squared equals 0. And this is the k equivariant version of the wave map equation. It also has a conserved energy, which is written here. It's 1/2 of dt psi squared r dr plus 1/2 dr psi squared r dr plus k squared over 2 sine squared of psi r dr over r squared. So here we have the volume measure dr over r, and see, because the integral is from 0 to infinity, this imposes some cancellation on the sine term. So you can see this, that I went too fast. Can I go back? Okay, for general wave maps from R2 into S2, the static solutions are the harmonic maps from R2 into S2, and these were completely described. There's a list in the work of Eels and Wood in 1976. And the traveling waves solutions to the wave map equation without symmetry are Lorentz transforms of harmonic maps. These are the analog of the bubbles of Karen-Uhlenbeck for wave maps. In the k equivariant version, they correspond to static solutions of the k equivariant equations. And these are explicitly given by kq of r equal twice arctangent of r to the k plus L pi, where L belongs to z. The one of least energy, which is actually the least energy harmonic map, regardless of symmetry, among all non-constant harmonic maps, is Q1, which is twice arctangent of r plus L pi. And because this is the one with least energy, we call it the ground state. This is a one equivariant, which is also called co-rotational, and this puts particular emphasis in the study of the one equivariant class. The well-posedness theory in the energy space for the k equivariant case is much simpler than in the general case, and was worked out earlier in work of Chatin and Tabildar-Zadeh in 1994. The issue of whether singularity could form for these equations was open for many, many years. In the equivariant case, blow-up can only occur at the origin, and in an energy concentration scenario, which is what bubbling is in this setting. The pioneering work of Struve from 2003 showed that if there is singularity formation, it can only happen by bubbling off a non-constant harmonic map. Later on, blow-up solutions were actually constructed by Krieger, Schlag, and Tataru in the case of k equals to 1 equivariant, Rodniansky and Sturbens for k bigger than or equal to 4, and Raphael and Rodniansky in 2012, again for k equals 1, but with further stability properties. There is a threshold conjecture in the subject for general wave maps, and this was proved by Sturbens and Tataru in 2010. And this threshold conjecture says that if the energy of the wave map is smaller than the one of the ground state, then the wave map should exist for all time and scatter. And by scattering, we mean asymptotic linear behavior. I will not say anymore. So this leaves open for, in the study of the dynamics of wave maps, the following questions. What happens when the energy is bigger than or equal to the energy of the ground state? And this you can address in different levels of generality. The most general case is for general wave maps, then for k equivariant wave maps, and then for k equal 1 equivariant wave maps, which are called co-rotational wave maps. An approach to these questions is suggested by the Solitude resolution conjecture. So now we're going to change gears and go to the Solitude resolution conjecture. And the Solitude resolution conjecture predicts that any global in time solution of a nonlinear dispersive equation evolves asymptotically as time goes to infinity as a sum of decoupled solitons, which is what is known as a coherent structure, and a radiative term, which is typically a solution to a linear dispersive equation. Solitons are traveling wave solutions which are well localized and travel at constant speed, which could be zero. So static solutions are solitons. For finite time blow-up solutions, a similar decomposition should hold, maybe depending on the nature of the blow-up. This conjecture, the Solitude resolution conjecture, arose in the 1970s from numerical computations and from the theory of integrable equations. So this started from a numerical simulation carried out at Los Alamos in the early 1950s, soon after the end of World War II, and which was the birth of scientific computation. It's the first simulation of a partial differential equation in a computer, which was carried out by Fermi Pascal Ulam. And in this numerical experiment, they encountered what they call the puzzling paradox. This puzzling paradox remained open for more than a decade, and until Martin Kruskal found an explanation for this paradox and linked it to the existence of solitons for a completely different equation, the corrective Riesz equation, which governs the evolution of waves in shallow channels. And it's an equation that goes back to the 19th century. After this discovery, Zabusky and Kruskal conducted another very influential numerical simulation, which showed the emergence of solitons and multi-solitons, which are superpositions of solitons and which are what are called coherent structures for the corrective Riesz equation. This simulation led explicitly to the Solitude resolution conjecture and also to the theory of integrable nonlinear equations, which explained something else that they saw in this numerical simulation, which was that the collision of solitons was elastic. That means that as two solitons come together, they interact and then they emerged unchanged, and nothing else emerges from the collision. And that's what is called an elastic collision. This was later understood to be a consequence of integrability. Integrable nonlinear equations can be solved by a reduction to a collection of linear problems. This is a very important class of equations in nonlinear science, but it is very rigid. It's very non-generic. Since the introduction of this Solitude resolution conjecture, this Solitude resolution has been proved in a few integrable cases. For example, in the KdV equation that I introduced a little bit earlier. The proofs are very challenging, even in this integrable setting, which can be reduced to a collection of linear equations. And there are issues that are still unresolved, even in the integrable setting of KdV. There have also been results in perturbative regimes near solitons, even in non-integrable cases. And this phenomenon of Solitude resolution seems to be universal. It has been observed numerically and experimentally, for instance, in the dynamics of gas bubbles in compressible fluids, and this you can see in a lab, and in the formation of black holes at the moment of gravitational collapse. And this, of course, you cannot see in the lab, but you can see in numerical experiments. The mechanism that one encounters in these examples for relaxation to a coherent structure, this superposition of solitons, and that is observed numerically and experimentally, is the radiation of excess energy to spatial infinity. So energy is conserved, but it is moved away to spatial infinity. Proving soliton resolution in a non-integrable setting is a major goal in the theory of nonlinear dispersive and wave equations. A far-reaching conjecture in general relativity is called the final state conjecture, states that the evolution of general sets of initial values for the Einstein vacuum field equations leads to the superposition of a finite number of Kerr black holes, or well-known black holes, which are the solitons in this setting, plus a decaying radiative term. This conjecture is currently completely out of reach. Nobody who's reading this or listening to this will probably live to see a proof of this, but it motivates the corresponding problem for simpler models like the wave map model. So let's make a pause. So up to now, what we have done is given the background of what we're going to do next, which is now we're going to do actual equations and concrete formulations. Okay. In the last 12 years, in collaboration with Thomas Duyckaerts and Frank Merle, and also with Howard Gia, Ivan Martel, Raphael Kot, Andy Laurie, and Wilhelm Schlag, we have been studying these issues of soliton resolution for wave maps and for the closely connected energy critical nonlinear wave equation. So the energy critical nonlinear wave equation is this following equation for real valued functions now. These are not manifold valued functions, these are real valued functions. And the equation is the D'Alembert, the wave operator, equal to the nonlinearity u to the power 4 over n minus 2 times u. And it's the initial value problem. Since we have two time derivatives, we prescribed two data, the initial data and the time derivative of the data. And we request that the initial data have a gradient in L2 and that the time derivative be in L2 initially. This equation also has a conserved energy, but this time the energy does not have a sign. So you have to deal with negative energies here. It's in this equation that with Duyckaerts and Merle, we introduced a method which we call the energy channel method to give a mathematical way to measure this radiation of excess energy to spatial infinity, which is seen experimentally and numerically. Now, let me show you the connection at this point between the radial nonlinear wave equation in 4 dimensions and the co-rotational or one equivariant wave maps. So recall that the one equivariant wave map equation is this equation here. K is 1, so this term is sine 2 psi of 2 over r squared. And when n equals to 4, the nonlinearity in the nonlinear wave equation is u cubed. Because 4 over n minus 2 is 2, and so we get u cubed. Now let me do the following transformation. Let me call u of tr psi, which solves this nonlinear equation, divided by r. And then there's this normalization constant, or 2/3. This u, if you write it, if you do the calculations, verifies this equation equal to this nonlinearity here. Now the equation on the left-hand side is precisely the wave equation on R4 restricted to radial functions. The nonlinearity you can calculate for a function capital U gives me u minus sine root 6u over root 6. And this lambda shares with u cubed the following properties. It is odd. And then by doing a Taylor expansion of the sign, you can see that for u small, lambda of u equals asymptotically u cubed to high order. And that's why the one equivariant wave maps and the energy critical wave equation in R4 in the radial case are very connected. Now let me switch gears and for a few minutes concentrate on the energy critical wave equation from R to Rn. And let me first describe what are the radial stationary solutions. They are given by this explicit formula, plus or minus 1 over lambda to the n minus 2 over 2, w of x over lambda, where w of x is given by this formula. Okay, this w of x comes from geometry again. It comes from the study of the Yamabe problem, which is the problem of deforming conformally manifolds to have constant scalar curvature. And in connection with this solution of this problem, this function w appears, and a nonlinear elliptic equation, which is the corresponding one to the nonlinear wave equation, appears. So the first breakthrough result in proving a full soliton resolution for nonlinear wave equations occurred in the radial case in 3 dimensions. And with Duyckaerts and Merle in 2013, we proved a decomposition. We decomposed that all solutions of the nonlinear wave equation, energy critical, can be written as sums of this W rescaled plus an error, which is a solution to the linear wave equation. And this holds for infinite time for all solutions of the nonlinear wave equation and for finite time for the ones that remain bounded in the energy norm. Now, what was the key point of our proof? And this is something that I want to emphasize, is that if you have a radial solution of the nonlinear wave equation in 3 dimensions, and it is not one of the static solutions, which are either 0 or plus and minus this W rescaled appropriately, then for either T, all T positive or for all T negative, there's always a residual amount of energy outside of a translated light cone. So the gradient of xt of u squared remains bounded below when integrated on the outside of the light cone for all T positive or for all T negative, for all other solutions. And of course, for u equals to 0, this is not the case. And it is not the case for the W lambdas by calculation. So this gives you a dynamic characterization of the solitary waves, in this case, the stationary solutions. And this energy channel to spatial infinity captures this observed radiation of energy to spatial infinity that is seen experimentally. There's always has to be this energy when you are not one of the solitons. So the proof of this channel of energy property relies on a corresponding proof for the linear wave equation on R cross R3. And that says that if you have a solution of the linear wave equation on R cross R3 in the energy space, then for T bigger than or equal to 0 or for T less than or equal to 0, the outside energy is here, is always bigger than or equal to something initially. And what is initially is the initial energy, but it's not for every solution. There's an exception for which there is no lower bound. And the exception is exactly the Newtonian potential, 1 over R in 3 dimensions. The fact that the Newtonian potential is an exception can be computed directly. And so we have to project away from the subspace generated by the Newtonian potential. And then we have this inequality. Now, this inequality is completely elementary. It could have been proved by D'Alembert in the 19th century. To use this linear inequality in the nonlinear case 1, the key point is that our soliton, our static solution, behaves for R large the same way as the Newtonian potential, which is the exception to the inequality 2. So the two things match. Now, in the case of non-radial solutions, this inequality 2 has a variant for R not equal to 0. And it says that for all odd dimensions, for all t bigger than or equal to 0, or all t less than or equal to 0, this outer energy without the shift in the cone still holds. And this is in a paper with Duyckaerts and Merle for 2012. Now comes the bad news. The inequalities 2 and 3 are false in all even dimensions, even in the radial case. And this we found with Kott and Schlag in 2014. And what happens is that this 3 holds when the dimension is 4, 8, 12 for data of the form V0, 0, and for the other data, for the data of the form 0, V1, when n is 6, 10, 14, and so on. And this is done by explicit examples. The family of examples is infinite dimension, of counterexamples is infinite dimensional here. And this is actually done by Fourier analysis. Now the inequality 2, let me go back to it so that I can remind you, is this one with this exceptional set. This fails in the non-radial case miserably for all n's bigger than or equal to 3. And there's an infinite collection of counterexamples, one for each spherical harmonic. Now, in the radial case, the inequality 2 has an analog for all odd dimensions, but you have exceptional subspaces of higher and higher dimension as the dimension n goes to infinity. So this kind of counterexamples got us stuck for many, many years. And we didn't know how to go forward. But nevertheless, we found some weaker results. And I'll go to those. We obtained weaker results using monotonicity after time averaging. This idea of using monotonicity after time averaging is inspired by corresponding work for the harmonic map heat flow that geometers had been doing for quite a while. And in the case of the harmonic map heat flow, they proved decompositions, but only for well-chosen sequences of time. They did not hold for all times. And we took the point of view of trying to imitate this approach and see if we could get something in this case. And the answer was yes. If we assume in the energy critical wave equation that the norm remains bounded in both a finite time or infinite time, decompositions for well-chosen sequences of time in the odd dimensional case was obtained by my then student Casey Rodriguez. And in the 4-dimensional case, it was in work with Kott, Laurie, and Schlag in 2014. And then for all n even, to finish the story, in a paper with in a known paper, in another paper with Gia, who at the time was my postdoc also. But this approach actually carried over also to the non-radial case in a paper with Duyckaerts, Gia, myself, and Merle from around 2016. But one has to be cognizant that this method of proof, which uses monotonicity after time averaging, cannot give a decomposition for all times, because Topping in 1997, for the case of the harmonic map heat flow, constructed a manifold M, which is not the sphere, but which showed that the decomposition cannot hold for all times. He showed that for different sequences of times, that phenomenon was different. However, it was conjectured that for the case of when the target is the sphere, this does not happen. But this is still an open problem today. Okay. So let me just tell you a few words as to what the time averaging does. Because there's an analog in calculus for this. This method of time averaging is analogous to when you have a series which may or may not converge, then you make the Cesaro means, and then you get convergence. And the Cesaro means and the time averages that we are considering here are related. Okay, so now let me get down to when we finally made progress in not just working for well-chosen sequences of times, but for all times. The first step here was in 2019. At the end of 2019, December of 2019, we posted 3 papers on arXiv, where we gave the full decomposition for all times for the radial nonlinear wave equations for all odd dimensions, assuming the boundedness of the energy norm. And how we did this is related to these energy channels, but it is also related to the Kruskal and Zabusky experiment, which, if you remember, I mentioned that showed that this, for solitons, for the correct Dirichlet equation, the collision is elastic, and the correct Dirichlet equation is an integrable equation. And these equations are non-integrable. And the philosophy here is that for non-integrable equations, there's always an inelastic collision. Something else appears after collision, which is not the same solitons. And that's what we proved for the energy critical wave equation in odd dimensions. And that also yielded the soliton resolution. Okay. So now let me return to wave maps into the sphere. And note that the fact that the energy norm is bounded is automatic in the case of wave maps, because in this case, the energy was positive and it controls the energy norm. So these extraneous conditions are not relevant. Okay. So the first works in the direction of soliton resolution were in 2 works with Kott, Laurie, and Schlag. Schlag was my colleague at Chicago at the time. Laurie was his student, and Kott was my postdoc at the time. And we established the decomposition for 1 equivariant wave maps, co-rotational wave maps, into the sphere under an energy constraint. So we said that the energy had to be less than 3 times the energy of the ground state. And this implied that the decomposition had only 1 bubble. Shortly after, Kott in 2015 extended this to general data without the energy constraint, but only for well-chosen sequences of times. Again, by taking time averages. And finally, soon after, with GIA, in the same work I mentioned before, we extended this to all K equivariant cases, but for well-chosen sequences of times, using monotonicity after time averages. And then it is interesting to note that Engelstein and Mendelssohn, a year ago, or a bit more than a year ago, almost 2 years ago, showed that in the case when M is not the sphere, you can manufacture an M like topping, for which the counterexamples of topping also exist for wave maps, so that you get the decomposition for sequences of times, but not for all times. Next, in the K equivariant case, Gentridge, who was my postdoc at the time, and Laurie also established the full decomposition when at most 2 bubbles appear. Now let me backtrack and talk about general wave maps into the sphere where there's no symmetry involved. Here, very little is known so far. Green in 2016 did obtain a decomposition for well-chosen sequences of times, but the error term is small in very weak norms, not the energy norm. And what we're looking for is for the errors to be small in the energy. With Gia, Duyckaerts, and Merle in 2018, we were able to show that if you increase the ground state energy by an epsilon, so this epsilon is this ground state energy, if you recall, is the threshold in the Stervan-Stataru result that says that if you're below the energy of the ground state, then you exist globally and you scatter. So if you go slightly higher by an epsilon, the energy of the ground state, you can decompose into scale ground states plus radiation, at least in the case when there's finite time blow up. But nothing else is known to this date for solutions without symmetries. So I next turn to our very recent results, here corresponding the full decomposition for one equivariant or co-rotational wave maps into S2. So this is the first unconditional Solitude resolution result for a wave type equation in an energy critical setting, because in the 3D results that we had for the nonlinear wave equation, we had to impose the boundedness of the energy norm for all time. Here, no extraneous assumption is needed. So to explain this result in the few minutes that I have left, we introduce the energy space. The energy space is basically the space in which the energy is finite. And it's not a space, a linear space, because there's this nonlinear condition. And let me explain that this nonlinear condition imposes something about the behavior of C naught at infinity and at 0, because if not, 1 over r dr diverges. So this has to kill 1 over r dr. And I recall that the one equivariant equation is this one. The K equivariant just has the K here. And the energy, which is this expression here, is an invariant of the motion. It's constant in time. So if our data belongs to the energy space, then it's easy to see that the limits as r tend to 0 and infinity has to be L pi and M pi for M integers because of the sign having to kill the 1 over r. And now we stratify the energy space by these 2 parameters, L and M. And so we call HLM the pairs psi0, psi1 in the energy space that have these asymptotics. And every element has one of these, belongs to one of these spaces. So this is an affine space, because you can translate by this, and of the following Hilbert space, which is like the energy space, but here we have the 1 over r squared, the potential 1 over r squared. Now, in this terminology, the ground state, which is twice the arctangent of r, belongs to H01 because of the limits at infinity, okay, of the arctangent, which we all know. And all the other stationary solutions are this rescalings of Q plus L pi. So the first theorem, which is from February of 2021, which also has Ivan Martel as an author, is that for all co-rotational wave maps in the energy space, it has a fine maximal time of existence. Then there are two cases. The final time is finite, which we call the blow-up space, the blow-up case. Then there's a constant pair in the energy space, which is the radiation term. There's a number J, which counts how many solitons come in. There's a sign, which corresponds to the plus or minus on the Q. There's scaling parameters lambda J defined near the final time. And this scaling parameters are decoupled, meaning that the ratios of consecutive ones tends to 0 as you approach the final time t plus. And the last scaling parameter is decoupled from the self-similar rate, which is t plus minus t. And our solution decomposes as the radiation term plus the sum of the rescaled solitary waves. That's the finite time. And the norm is the norm of the Hilbert space H that I defined before. And then for the global case, the radiation term is now a solution to a linear wave equation, which is the one associated with the Hilbert space H, where the potential is 1 over r squared. And we have a solution, a linear solution with initial data in this Hilbert space H. And there's the parameters. Now the self-similar rate going to infinity is t. And so we have scaling parameters. And we have our solution is the linear solution minus the stationary solutions rescaled. And then one can show actually that there's some compatibility conditions between the various waves having to do with the behavior at infinity. Now, this theorem follows from what we call a rigidity theorem, which is a channel of energy theorem. Suppose that that's theorem 2. It says that if I start out with any element in the energy space, which then belong to some HLM. And suppose that C, the solution C, is not a stationary solution. And this is the description of what the stationary solutions are. Then, if you look at the outside of the light cone energy, then either for T positive or for all T positive or for all T negative, this remains bounded below. So that's the radiation of energy to spatial infinity. And this is our tool to show that the collisions of solitary waves are inelastic, so that there's always radiation to spatial infinity. And finally, I conclude by mentioning that more recently, in fact, it was posted a few weeks ago, the end of June, Gendron and Laurie extended the decomposition from the k equals 1 case, the one equivariant case, to the general k equivariant case. And so with that, I conclude the talk. Thank you very much for your attention.
Okay, Carlos, thank you very much for the nice talk. Now we have time for some questions or comment. So if somebody want to ask a question or make a comment, just please raise a hand. That is this icon that is in the lower part of the screen, and we will authorize to speak. That's how this system works. So I don't see any hands so far. Okay, so they tell me here that you also can ask questions using the Q&A icon that is also in the lower part of the screen. I think there is some.
Yeah.
Okay.
Should I go to that? Okay.
Okay, Suzanne Lenhart.
Oh,
Thank you. Thank you.
Thank you.
Okay.
Hi, Suzanne. Thank you.
Okay. Let's see if there's something else. I think not open question anymore. Okay, so I think if there are no questions, thanks again, Carlos, for this great talk and for accepting giving this plenary talk. Thank you, Carlos.
It was my pleasure.
Oh, there's a new message here.